Hello everyone, welcome to our next special episode of Conversations about the Cosmos. My name is Samuel Kovacic. As always, Norby Werner is here with me. Hi.
Hi. Hello, hi.
And we have a very special guest, Michel Mayor. Have I pronounced it correct?
Happy to be here. Mayor. Yes.
Mayor. So just to introduce you a little bit, you are, among other things, a recipient of a Nobel Prize for Physics for the discovery of the first exoplanet that orbits a sun-like star. What was the feeling like to be the first to know that there are probably a plenty of other planets?
Not probably. We already have more than 5,000.
We already know. But when you discovered the one, that was...
So, it's an interesting question because, in fact, I start my life as a theoretical physicist. Density wave in the galaxies and so on. A completely different story. And then after I was driven by the development of the technology, spectroscopy, high precision spectroscopy, and some moment, the second generation of instrument we have developed arrived at the level of the possibility to detect planets. And by chance, I attended a conference in the French Alps on exobiology. And it was for me the first time I met this kind of people. And I realized, oh, interesting question. And a couple of years after, during the commissioning, the first measurement with this new instrument, we arrive exactly at the level we need to detect planets. So it was a natural path to go, okay, we have a new instrument with this precision. We will not continue to do what we made with the previous instrument. So what's in planets search? But at the time, the paradigm that to form giant planets, like Jupiter, you need to agglomerate ice particle. And ice particle exists only at distance large enough to exist. So this corresponds to orbits with a period of more than 10 years. So when we start our program to search for planets, okay, it's 10 years it's a long time before publishing anything. And at the time in the 90s, early 90s, another category of object was already a hot topic, was brown dwarfs. Brown dwarfs were so small planets that the mass was not enough to ignite nuclear reaction in the core, but they are formed like stars by collapse of clouds of gas. So, and at the time, nobody knew what was the formation process exact and period and so on. So we wrote the proposal to have time, say we would like to search brown dwarfs and giant planet. But in our mind, we say probably we will start discovering brown dwarfs with short period. And after only a couple of months, the first in our measurements was an object with a mass of about half the mass of Jupiter, but with a period of 4.2 days. So it's a small discrepancy with the theory. It's a factor 1,000. Between 4 days and 10 years, it's about 1. So you have to be careful because the domain of the search for exoplanet was really badly considered in the community of astrophysics because already from 1943, 2 papers was published claiming the discovery, and 1 year after it was shown it was only technical problem, and then after have a lot of different claims like this. So when you discover an object with a discrepancy by factor 1,000, okay, you have to be a little bit careful. So because what was the reason? Okay. The technique we have been using was to search for the reflex motion of the star due to the orbit of the planet. So we cannot see the planet itself, but just to see the small wobble. If this is a star, the planet orbit like this, so you have a small change of the possibility of the position and the velocity of the star. Okay, but as the ratio of the mass between stars and planets is so huge, so the change of the velocity of the star is very, very small. You have to design a spectrograph with the capability, the sensitivity to detect extremely small change of velocities. So it was a technical difficulty. The idea was already proposed many years before, but at the time we have no technical possibility to do it. So what are the... Okay, one possibility to change the velocity of star if you have a planet or a star or a body. But another possibility, when you have the star with spots like the sun, and the star is rotating, so due to the spot, you have apparently a change of the velocity. But it's nothing with the planet. It's only a noise due to the magnetic field of the star. Another possibility, you know that you have some pulsating stars. So if you are looking at the surface,
it's moving,
you have also a change of the velocity, and so on. So it's a reason why we have to be careful. And so I've decided, because I have two young collaborators, but okay, this kind of decision is the responsibility of the boss. So we have decided to postpone the announcement until the next season. And 51 peg reappear in the sky in July the next year. So we wait, we ask time, and we have remeasured the sea and to see if we are following the ephemerid determined from the previous season. But it was not so luxurious. It was, the first season was only 12 measurements. 12 measurements, 6 free parameters. Okay, we are not so comfortable.
A lot of moving.
Yeah. So we extrapolate the orbit and we check in July 95 the period, the phase, and the amplitude. And the result, it was okay. So after 1 week, 7 measurements, okay. No, it was more because we repeat the measurement. But after the week, we are convinced nothing changed. So pulsation was eliminated for different reasons. I will mention after. But the magnetic field, okay, you know the spot of the sun are moving towards the equator, and the sun is not a solid body, so you expect a change of the period, and a change of the phase, and a change of the amplitude. So this is a test to eliminate this problem of the pulsation. In fact, to have a pulsation at 4 days, this would correspond to a gravity mode. And a gravity mode with 4 days of period is needed with a pulsation, a gravity pulsation, with n, the number of nodes, of 114. Large amplitude, 114, one single mode excited. And in fact, people have searched for gravity mode in the sun, and it was not observed. So the theoreticians of the pulsation of stars say, no, it's not possible. So, okay. So in July, we are sure it was something. Okay, we have to solve what? Because if it's 4 days, okay, we have to solve. And we still have one problem. It's the problem of the orientation of the plane, because we measure only the minimum mass. So some of our colleagues say, okay, it's a normal object, the binary stars with a very perpendicular line of sight. Yes, but in such a case, you will have a stellar companion close to the star, and this will create a strong magnetic field. And we have not observed any strong activity. So, okay, it's normal physics. Eliminates the possibilities. And so we published in October. We first announced the discovery in Florence, Firenze, in north of Italy, during a colloquium in October 95. And then this was published by Nature in November 95. So this is after the beginning of a tough period with media.
So very methodically, you just crossed out all other explanations.
Exactly.
Then you were...
Exactly.
100% sure, or still a little bit doubt left that maybe something simply have been
you are
overlooked?
never sure that you know all the possibility of physics. You have the only answer I can say, I don't see other reasonable things.
Yes.
And when I present the things in Florence, it was a Cambridge workshop. It's moving. It's solar physics and low mass stars and so on. So 300 colleagues working in low mass stars. And among the participants, you have two of my colleagues. Is Volger, he was the boss of ESO, and Franco Pacini, the director of Firenze Observatory. Very good colleague. And I discussed at the coffee break and say, if you are safe with your measurement, don't mind. Publish it, then after we will look for what is the correct explanation why we have this discrepancy of 1,000. So it's but not everybody was convinced at the time.
Of course,
some of them was no, it's not planet, because they prefer to look on the theory. And after 1 week after the publication by Nature, 3 of our US colleagues, Douglas Lynn, published a paper in Nature, so it was very quick. 1 week after it was submitted. It was published in 1996, but it was submitted 1 week after, giving the answer, the explanation for the short period. And it was maybe one of the most important things, because when you have a disk of dust and gas surrounding the star, and you have a young planet starting to be embedded in the disk, in fact, you start to slightly modify the density of the disk. And the small modification at the resonance place in the disk react on the orbit of the planet. And if you integrate this after a very short time, much too short, whoop, you have spiraling close. And this was already studied in 1980 by Goldreich and Tremann. It's a big name of the theory. And nobody take into account this fact. It was 15 years before. And I discussed with Scott Tremann, say, why? Nobody take it, because it was too efficient, and because the time scale of this phenomena is so short that we say, if not, we will not have any planets. And in fact, what the paper published after the discovery of 51 back, evident taking in facing the reality, that they discover the phenomena to stop the migration. So the migration stop close to the star by different process, magnetic field with a cavity and so on. So this is a story. And the net result for us is that first, sometimes people say, like you, have you been happy with it? But it's not one specific moment, because it's a long process. You are doing measurement, you start to see that maybe you have a periodic thing, and then after you confirm and so on. And it's only after a few months, okay, yes, we have, but it's not, okay, today we have discovered planet.
So I would like to ask you two things here. One, that in astrophysics, the progress in astrophysics is today driven by technology. And when I look at your career, you were studying spiral arms of galaxies, and then you started the development of spectrographs, and you participated in a development of a spectrograph that achieved a precision in radial velocity of 1 kilometer per second, and then came LOD, which had 15 meters per second. And eventually harp
1 meter per second.
Yeah.
And espresso, but espresso was not my work. It's 0.1 meter per second.
So it's a huge.
Yeah.
So what was it that drove you during that technology development? Did you have in mind that you want to discover an exoplanet? Because what you discovered was unexpected. You didn't expect to have a hot Jupiter. That was not something you probably had in mind. So what was it that drove you?
Yes. First, the first step, then it was a nice meeting with a colleague in Cambridge in 1971. It was during the coffee break of a meeting devoted to theory, dynamics, gravitational interaction. And at the coffee break, they offer the possibility to visit different dome. And okay, the theoreticians are not really interested by this. But I did. And I met Roger Griffin in a dome, and he was developing the first very simple cross-correlation spectrometer. And for me, it was really, this is a good idea. Mm-hmm. When I went back to Geneva, I asked the director, because just after my PhD, I asked the permission or the support to build a new spectrograph, because it was, also for a situation, it was easy to imagine something better than the first instrument made by Griffin. He do it with very simple, no support, technical support and so. So we start the construction with an instrument with a computer control and many different kind of optics and so a lot of improvement. And it was extremely successful. And this immediately, okay, you see that the efficiency of this new spectrograph was more than 4,000 better than the old photographic plate measure of Doppler shift. When you have an instrument with a gain of efficiency of 4,000, you don't need to be clever. You can investigate every domain. You have a gun much better than the others, and so we have made work in the pulsation of stars, rotation of stars, dynamics of globular clusters, and so on and so on. And part of this was we decided to revisit the domain of double stars. It looked like to be very old astronomy. Okay, it was not really considered. We have defined a good sample of stars in a volume close to us, and systematically during more than 10 years, we have measured the velocity of the star to have the distribution of mass, distribution of period, distribution of eccentricity, and so on. I was not interested to discover new binaries, but to have a good constraint for the formation of stars, planet, because most of them are formed in binary system. And so we accumulate a huge amount of data with the old spectrograph, the first one, Coravel built in the 70s. And during many years, this paper was a number of the impact was larger than the paper by the discovery of 51 peg, because it was so systematic. But evidently, due to the precision of this spectrograph, we were limited to the detection of very small objects. So when, in the end of the 80s, the director of the French Observatory, Haute-Provence, asked the opticians, André Baran and myself, do you want to develop a similar instrument, but to be put on the bigger telescope, 2-meter telescope at Haute-Provence? But during this almost 20 years of development, new technology appear. Large CCD, optical fibers, and other things. So they say, oh yes, we can do. And so we design a new spectrograph, taking into account this kind of technical. But it's very difficult to, what you will, comment dire, what will be the improvement of the precision? Difficult to do a real model of the what. It will be better. and then we start the commissioning with Didier, and we achieve immediately the first night something like 10 meters per second. So it was with the old Caravelle it was 300. So when you have a factor 30, you say, well, I will not continue to do dynamics of globular clusters. What we can do, and you say, okay, planets, and so this is. I was not really interested in planet before this moment. Okay, just like any astronomer. Okay, and this is the path of the. And then after once you have discovered the first one, okay, you put everything away except this domain, and you start you put all your energy to explore this domain, to ask for more time with the telescope, because at the beginning we have only 1 week every 2 months. For the standard in the 90s, it was considered as a big program. So 1 week over 8. But for the modern requirement for planet search is nothing. It's not because you see, you do some measurement after you have wait 2 months, and then after you have rains and so on. After the star disappear of the sky, you have to wait 1 year. Okay, so you see, and so immediately after the discovery of 51 Peg, I asked to have twice the more time, so 1 week every month. So for 25% of the largest telescope, when you are not French, okay. But okay, we have extended the number of collaborators to 7 people, with people from Grenoble and other place, because and so immediately we discover a new kind of object, very interesting one. When you have the power and observing time.
Can I have a brief question about the pivot in your career? Because I'm a theoretical physicist. And when I hear that somebody is developing a new telescope that can observe something I'm trying to study, my reaction is, well, good job, I'll wait for the result. Let me know when the telescope is ready. But you basically pivoted from theoretical physics and doing observation to actually developing the instruments.
Yeah.
Even though it may be 1 or 2 degrees of separation from your area of expertise. So what gave you the confidence that you will be helpful in this regard, and you shouldn't be waiting for the result, but help it bring forward?
Yeah, first is very nice meeting with Roger Griffin. I fall in love with his technique. Immediately, see, you know, in the spectra of low temperature stars like the sun, you have several dozen of thousands of atomic transition. So it's a forest, a huge forest of atomic transition. And the old technique was to measure the change of the velocity of this line, this line, this line, on emulsion moving, which was very difficult. So it was using only a tiny fraction of the Doppler information. So the idea proposed by Felget in 1995 was to try to build a design, technical design, to concentrate all this information on one line, and to search for the velocity. And it's nothing magic. It's simply you have to build a template. It's almost something like almost the negative of the spectra. It's a little bit more complicated, but something like this. And then you put this negative in the plane or in the surface of the detection of the instrument. When you measure, you project the spectrum of a star in front of this template, and you are doing this thing. You measure, and you look what is transmitted, and the lower transmission luminosity transmitted correspond to the best fit between the two, and is a position corresponding to the zero velocity. or to the velocity of the star. So you are using the information of several thousand of line in one, comme ça. And more, we are using a photomultiplier, and the quantum efficiency is something 10%, let's say, at the time. So the emulsion, photographic emulsion was 1%. So it's already a factor 10. The computer, you can accumulate. And all the work is done by the computer after to reduce the measurement. And so this is part of the huge gain of efficiency. And when you are using after a CCD, you still have a gain, because the quantum efficiency is 80% and not 10%. So another factor of 10. So it's so efficient. So this is, and I was a little bit naive when I decided to build this instrument. So, okay, something I can...
This always helps being a little bit naive.
And so I opened a book of optics, and I say, what is the best design for the spectrograph? First chapter, oh, wow, it's great. Second chapter, oh, it's the same, it's great. I do not have the background to choose what is the best optic. So I've decided to call André Baran at the Marseille Observatory, and I have a meeting to him, and I was just looking to have some advice, nothing more. And I have a meeting with him, and he said, oh, interesting, I will do it. I will not give you advice, I will do it. So it's a start, and we have been working 30 years together after. And he arrived with very clever idea, evidently much better than I can dream to have. And he did the optics. And then after, I was in charge of the cross-correlation to build the template, because to optimize the template and all around and so on. And this is the start of this adventure. But and it was a good idea to change, because I was supposed, after my PhD on density wave, the mecca of the density wave was MIT in the US. So I got the money to go to work in the MIT. But just in the between, I have this meeting with Griffin in Cambridge. I say, oh, I will build it. So I have to change the destination and allow me to go to work with Griffin during 1 month, and after to start the construction. And these people agree.
Great.
So it's and then after it was during the very first 15 years with Corravel, with the very first instrument. Okay, it was maybe I work in too many domains because it was so easy. But some of them was good. But the problem was the density. The dynamics of globular clusters was fascinating, because it's a very interesting object. Globular clusters, sometimes it's very simple. And do you have some segregation of objects going to the core, and maybe to form massive object, maybe black holes? And this was the time where you have X-ray emission detected in globular clusters. So is it black holes? In fact, it is not, but it was binaries, only binaries. But okay, this opened the interest for many, many different and binaries, the old binaries.
Yeah. So with the LOD, you discovered the first exoplanet, a hot Jupiter, something that people didn't expect to find. But then with HARPS, you found the first super Earth in a habitable zone.
Yes, and okay, maybe okay. Just after the discovery of 51 Peg, ESO asked people interested in detection of exoplanets for a brainstorming meeting. And you have some people say, oh, we have to detect this kind of technique, the other this, and they arrive and say, oh, maybe we can build a new spectrograph with a better precision. And as already at the time, the typical precision achieved was 10, 15 meters per second. So the ESO had not to develop a new instrument with the same domain of precision. We have to fight to go to 1 meter per second. But of course, it was a little bit easy to say this. And 1 year after, ESO issued a call for tender. Who are interested to develop a spectrograph with a precision of 1 meter per second? Wow! And we have been the only one to answer this call for tender, and we start to see what we can do, what are the weak points of LOD and so on, what we can do, and we have proposed vacuum and many other small improvement for that. Okay, some of them are not so easy. Okay, and I heard some good collaborators, for example, Francesco Pepe, the present director of the observatory, and we start the construction. I believe it was really a success, because from the time we signed the contract, it was written that we should have the first measurement 3 years after, and with the proving to have 1 meter per second. I believe it was one of the only instruments having respected the delay. Exactly 3 years after we were on the telescope in Chile. And we proved it was 1 meter per second. So the reward was not bad. We got 500 nights of big telescope. So it was, okay, a good contract. So 100 nights per year during 5 years. And this was absolutely fantastic, because you need to have not only a precise instrument, but to have the continuity, to have the sampling. If you have precise measurement, but one every month is not enough. If you have multi-planetary system, it's not enough. You can. So with this huge amount of nights, we have detected the population of what is called super Earth and Neptune-type planet or short period orbit. And already in 2008, so it was only 4 or 5 years after the beginning, we got already 45 objects in the range of mass, just above the mass of the Earth. And it's a population of super Earth. And part of them, one was Gliese 581 with one planet part close to the habitable zone and so on. So this was a very interesting moment. And also, I mean, in the progress of this kind of survey, we have discovered quite few quite interesting objects. And for example, HD 209458, it's one of these objects, magic object, because it was an object very bright, with a period of only 3.5 days. So we have decided to search, as we did before for other objects, to search if we have the chance of transit. Because if the orbital plane is good, in fact, you have a transit. But evidently, if you are not aligned with the direction of the telescope, it's not working. A priori, you have no way to decide. But you know, if the plane is correct, you can decide exactly at what time this appears. So we were collaborating with people at Boulder Observatory, and Timothy Brown and David they made the observation, and the 9 and the 16 of September 99, we observed exactly at the time predicted by the FM. we observe the transit. A decrease of the luminosity by a little bit less than 2%. Okay, 2%. The radius or the diameter of Jupiter is about 1/100th of the 1/10th of the diameter of the Sun. So the surface of Jupiter is 1/100th of the size of the Sun, the surface of the Sun. So let's imagine you look Jupiter crossing the disk of the Sun, this will induce a dip of 1%. So if you know the size of the star, you have the size of the planet. So, and if you have the size of the Doppler, give us the possibility to determine the mass of the planet. The transit gives the size, so it's not difficult to have the mean density. So, and we tried for this star and the result was a density of 0.3 gram per cubic centimeter. So it's equivalent 1/2 of the mean density of Saturn. So it was really a direct proof that it was really gaseous giant planet. And because the last skeptical of our colleagues, and still is, some of them exist in 1999, was only really convinced that it was a giant planet. And this was also independently measured by the other team, Jeff Marcy and Paul Butler. And in November, they measured the ingress only because the star was disappearing. So they were only able to measure the beginning of the transit. So this was the start of a new big adventure.
And then Kepler was launched.
Corot, TESS, and many satellites was. And this is a fantastic mean. And but okay, the deep in medium wavelengths give access to the size of the planet. But this is not the most interesting thing. When you have a small drop of the infrared luminosity, when the planet is behind the star, so the drop of the diminishing of the infrared luminosity gives the temperature of the atmosphere of the planet.
This was measured with Spitzer, right?
Yes, exactly. Spitzer have measured this already in 2006 or something like this. But the more interesting thing is the fact that when you have the planet and you have a small atmosphere, and the atmosphere will filter a little bit the luminosity of the star. So when you compare the luminosity, the spectrum in front and behind, you have access to the information due to the filter made by the atmosphere. So you can repeat it for different wavelengths. And let's imagine, to explain the idea, it's very easy to understand. The size of the Earth is something like 6,000 kilometers, the radius. 6,000 kilometers. Okay, in the visible. So the decrease of the luminosity of the Sun in the transit will be characterized by the size of the Earth. But let's imagine you repeat the measurement at a wavelength in the infrared at 9.7 micron. This is a wavelength due to the absorption of ozone. Ozone is stopped at 40 kilometers away. So the size of the Earth looks bigger. So if you repeat the measurement for any kind of wavelength, in fact, you measure the opacity spectrum of the planet. So you have the possibility to start to do chemical analysis, modelization of the atmosphere of the planet. And this is what is going on. And if, you have this beautiful achievement already made, in particular with the James Webb Telescope, where several, for the moment, is molecules also. But if you need a lot of photons to do it. So when you increase the number of photons, you will have access to higher resolution. And so maybe you have the chance to detect biomarker. So molecules related with the chemistry of the development of life. So this is the most promising avenue to search for existence of life, to search for what is supposed to be real signature of the development of life. This idea started already 30, 40 years ago with the fact that people question the fact that 20% of the atmosphere of the Earth is made from oxygen. And okay, we learn this at school, okay. But in fact, it's absolutely not so evident. Yeah. Because oxygen loves to do oxides with rocks. And so if you kill everything, every form of life, after a few million years, we will have only maybe 1% of oxygen. Okay, you still have some possibility to form oxygen, but at very low level. So because anytime you form oxygen, it disappears in oxide. So you need to have a very efficient mechanism to form oxygen. And the only apparently efficient one is related to the life. So this was considered to be a very strong biomarker. So at the present time, evidently, this is a typical development of the science. You have people looking, maybe not. Maybe we can have alternative process not related to life. So, okay, it's still open a little bit. Personally, I believe it's related to life, but okay. And then after, you can look for other molecules, methane, nitrogen oxide, water, evidently, CO2, and so on. So it's not an easy answer. It's no more a problem of astronomer. It's a problem of chemists, biologists, and so on, to start to accumulate a certain of observation, saying, it's probably the best explanation is life. So it's maybe, but it's still a very open domain. We are not sure that what could be the most significant biosignature.
And this always gives me goosebumps, just realizing that we can actually measure atmospheres of exoplanets, which is
we still not
totally
have the possibility to see them, but yes.
And is there any chance of detecting some structures on the exoplanets? For example, seeing that this part is cloudy, or there is some source of lights, maybe, or forests, algae, something like that?
Yes, I have some colleague having made some experiment, apparently very simple. You measure the reflected light from the moon. You have the light coming from the sun and illuminates the Earth, and the Earth illuminates the moon at some phase of the moon, and then you can measure the light reflected by the moon coming from the Earth. And this is affected by the fact that you have big forest. So because if you are, the photosynthesis will induce a drop in the infrared. So if the reflected luminosity of the moon at some moment gives the possibility to detect that photosynthesis exists on the Earth. So you can have evidently the same idea to look for during the orbiting of planets to see exoplanet if you can detect something similar with is not done at the present day. The precision is still But you see, without detecting the planet itself, you have also some dream related with the polarimetry. Okay, it's because also you have polarimeter change of the polarimetry of the luminosity, and so on. You have different. Okay, in principle, you have access to some more detail that exists, but you need a lot of photons. And you have some people working evidently for the direct imagery. It was not possible 28 years ago or something like this, but today we start to have some image of exoplanet. But the planet detected up to now are mostly massive planet at some distance, maybe some big distance. So they are not related to life. It's a difference. It's interesting, but it's not related to this kind of question. But this opens new interesting field, because when you have a star here and you have a giant planet very far away, what is the mechanism to form a planet so far? You have almost nothing to agglomerate. So maybe they are formed by different process, something like a star, instability in the disk of dust and gas. So this is also interesting, but it's a different story. I believe for the planet having the capability of life, we are still far away of the capability to detect, really do the images of planet. Okay, you have some people looking for the future, long-term future. And for example, if you have people studying the possibility to have extremely distant satellites, 100 kilometers. And if you have a planet here, you can you can dream to have a perfect alignment between this satellite and this detector here. And maybe with a relatively large disk here, and you do an occultation and to try to see the planet, just to stop the light from the star, to see only the planet, and do the spectrum of and see the. This is long-term future. It's probably feasible, but it's not easy to do it. You have to align at the level of the 1 second, or no, much better than 1 second, to satellite 100 kilometers. Okay, probably it's feasible, and you have people looking for this kind of possibilities.
So if someone was looking at our solar system, he would see Earth casting basically a very small shadow, but also another smaller shadow from the moon.
Yes.
And sometimes we should be sitting on a line, so you see only the Earth shadow, and you can maybe conclude that there is a planet and a moon. So can we actually detect exomoons?
You have, I don't know exactly the most recent result, but you have some claim of the detection of satellites, at least one. But okay, it's not completely so clear. Okay, but the idea is very simple. You have two different techniques. One, when you have a star, and let's imagine you have the Earth orbit the Earth. So the transit will be perfectly periodic for the gravity center of the Earth moon system. But due to the fact that you have a moon, it's it's about 10 times less massive than the Earth. So sometimes you have the gravity center is periodic, but not the transit due to the Earth. So sometimes the Earth is in advance or in return.
Okay.
So this you can detect satellite. The other possibility, when you have the transit, you have the shadow, the deep of the star, and you have a small one due to the satellite. So this is the two techniques. And okay, I'm sure that it will work. Okay, I'm not so fan of this because if you form objects in a disk, always you have some object. You see, Jupiter has a lot of satellites. the Earth as a satellite, two are on Mars, Saturn has satellites, Uranus has satellites, and so on. So it's so natural project. So let's imagine you detect one. Okay. It's interesting, but because maybe we have different ideas after, but is it really the most urgent point? I don't know. But it's nice.
So you mentioned a lot of meetings that started, basically pivoted your career, gave you a good idea, started basically a new technique. Now you are doing also a lot of outreach, like you are now in Slovakia, you are the head of the committee for the Asset Science Award, and hopefully returning next May for Starmus. So again, a lot of meetings. Is having a lot of meetings necessary for doing science and for young people to meet other scientists? Why do you value this so much?
Yes, I'm still a little bit involved in real research because my young colleague don't push me away.
I don't want to say that doing science outreach means not doing science, because
okay, I would say okay, we agree. But at the present time, I devote most of my time to outreach activity. And for example, I've been in Armenia, and I made one conference, a lecture, inside the main meeting in Yerevan, but several others in university, high school, in different places. And very frequently I made this. And for example, in La Réunion, in the island of Sun, I made several conferences, and not me alone. It was during a conference with a dark side of the universe. So you have cosmologists and things like this. And all the participants, French-speaking participants, gave lecture in school. I had 60 different lectures. And it's incredible because, for example, you have lectures given by on problem of dark matter, of Higgs boson. And so you see who will be interested in this place. And you,
I would.
2 hours, yes, you, but two hours of lecture in question of people. So it's the quality of the speaker to have the capability to stimulate interest of these people. So, and this is what it was done in Armenia, where we have, I don't know, 80, not me, but all the speakers devote quite a lot of effort to do it. And presently I continue to do it, and with pleasure. It's nice to have the reaction of young people. Okay, adults, it could be also it's different, but when it's children, it's or young students, it's good. It's interesting. And for example, I would say a reward of the Nobel Prize. Several times, but still recently, I received an email from China. He said, in 1995, I was 10 years old when I learned that you have discovered a first exoplanet. I've decided to become an astronomer. And today I am. Okay, this is... and I'm convinced of the outreach, the need. And also I have some activity in a different domain, but related. In Geneva, they have founded a meeting, international meeting, to try to do some perspective, what science could bring on the society in 5 years, 10 years, 25 years. And to bring this information to the government. It's open, it's not... And this something like 1,500 scientists in the world, quantum technology, pandemic, and all the things we believe could have an impact on the society. It's a huge effort, global, of the community I'm a little bit involved in this, in this thing. But it's interesting. Maybe it's completely wrong, but it's not a problem. You see, the internet was not anticipated before. So, do we are able to anticipate? I don't know.
So the outreach is not only about keeping the inflow of students into astronomy, but also about informing other people about the values of science.
Yes. I believe it's not a problem to increase the number of astronomers. I believe it's really this. And I'm sometimes surprised. I was invited to the Swiss television for some kind of game. It was built by people related to economy. So be cautious. And the frame of this emission was they proposed to the public a sentence I have said, that they choose we need to increase the money devoted to fundamental research. And do you agree or do you not agree with that? And then after I have a discussion with a lady of the mission, and at the end of the mission, for 30 minutes after, they look and I believe the lady was sure that it will be devastating. Because they mentioned several times, so many billion are given to the research in Switzerland and so on. So, inducing the idea that is enough. And she was extremely surprised that at the end, 80% of the people say, yes, we have to increase the quantity of money. I was a little bit, promoting the idea is not an increase of the money for astronomy, but for fundamental science. And I say, for example, biology, we still have some, it was before the COVID, but we need to solve important problem. In biology, you have the problem of the cancer, for example, and other things. So, and this will be coming from fundamental research. And in principle, 80% of people agree with the idea.
Well, you were correct. So nearly we ran out of time, and the things you're doing brought many people to science. So maybe a very weird last question. What brought you to science?
When I was a kid, I was interested in science, not specifically in astrophysics. I was really, at school simply, I was really interested in science. And for example, I was living in a small town in the Upper Rhone Valley, where you have a mountain with a huge Z like this due to the tectonic. I don't know the name in English. It's due to the...
Yeah.
Yes, okay. And then you see, when you have a kid, you look this, it's possible that you can deform the rocks at this level. This is just one example. And then, I did high school in science and so on. And then after, it was the moment to start to choose at the university. And I was attracted by theoretical physics. So I did my master in theoretical physics, interaction of particle with large spin, and it's nothing with astrophysics. And then it's so, but I start the university with mathematics and physics. The first year it was possible because the number of courses was not excessive. And then after 1 year you have to choose. I chose to do theoretical physics. I don't know if you know the name of Stuckelberg. Stuckelberg was a collaborator of Feynman. It's a group of renormalization and so on. So this was my most important teacher, and so it was fascinating. So, and you have good teacher. Sometimes critics, teachers, not me. You have some better than this, but I've been lucky to have absolutely fantastic people.
For example, it all started with a Z-shaped Wally you saw.
And also the professor of science when I was between 12 and 16 was an old man, very formal dress, and he was the director of the school where I was. He was teaching physics and biology and anything like this, and all his life he continued to study nematode for free, just for the pleasure. He was an expert at the international level of nematode. It's this kind of worm you can have. And created illness as well. And he was so happy when he received some dirty water coming from Africa and so on. And he was so, all his life he continued at home to study this thing. It's a pandemic, you see. Well, he communicates the interest for science. And I'm not expert in nematode, but a little bit. Because as all students at the time, he shows the interest, the magic you have, receiving water from underground, where you can find nematode below, and so on and so on. So when I started the university, I did physics. But let's imagine that at the end of the university, I saw two advertisements. One in statistical mechanics at the École Polytechnique, one in astrophysics at the Geneva University. We were both working on interaction of particles, and we discussed in the bistro where we were together. What do you prefer? And I say, maybe I would go and discuss with this place. And I say, I will go and see the other one, and after we will see. And I went to the observatory, and I was really interested in what I have to do. But let's imagine this day, we'll have an advertisement to do geophysics. I will have made geophysics. I do not believe I'm less interested in one domain or another. You have to choose, but astrophysics was only one. Science is exceptional in every domain. For example, last week, I heard that a group of the University of Lausanne, or École Polytechnique of Lausanne, was able to detect in some place of the dinosaur, a fossil of dinosaur, some small piece of stone or thing erupted by the collapse of the impact of the Crétacé tertiaire 60 million years ago. This was absolutely proof that the dinosaur was killed by the dust emitted by the. It's so fascinating. So for me, it's exactly at the same level of exoplanet. I don't believe one is better than the other.
So people just in general should be very curious and observant. And
yes, it's all. And in fact, in some sense, we are really happy to do science.
We're very privileged to do so.
Yes, it's a privilege. It's a huge privilege to do this. And all my children are doing science. I never try to convince them at all. They choose their own field by themselves. They arrive at home and say, I would like to do this. Okay. But evidently at home, we have frequently colleagues coming from different domain of science. And the kids are listening what this guy. Because I was, during several years, involved in a society outreach of science. We organize 6 conferences for the public during the winter, any domain of science, and a certain number of excursions in the summer, in the Alps. And I was president of this society during a few years, and the duty of the president was to invite for the dinner the invited person, and this was the occasion to discuss with these people at home, and the children was listening what they're saying. So I believe it's nice, and I cannot understand why we don't have so many more students.
So unfortunately, we probably ran out of time, and we don't want to basically take too much of your time because you are very busy these days. So thank you for coming and basically being an inspiration to both of us, but also for our listeners. You radiate curiosity, and basically it's very obvious that the defined science, fascinating subject, and a marvelous thing to spend your life on. So thank you for coming.
Thank you very much.
Merci beaucoup. Thank you.